Hello and welcome to Talking Papers, a podcast where we talk about papers and let the papers do the talking. Today, we will be talking about the paper Neural RGB-D Surface Reconstruction. This paper was accepted to CVPR 2022 as a poster presentation. And I have the first author of the paper, Dejan Azinović. Dejan, welcome to the podcast. Can you introduce yourself?
It's a pleasure to be here today. My name is Dejan, and I'm a PhD student at the Technical University of Munich, supervised by Professor Matthias Nießner, and working on visual computing and artificial intelligence. My areas of interest are computer vision, computer graphics, and deep learning, and I work on methods that lie on the intersection of these three fields.
Who are the co-authors of the paper?
The co-authors of the paper are Justus Thies and Matthias Nießner, Ricardo, Martin-Brualla, and then Goldman. This was a collaboration between the Technical University of Munich, the Max Planck Institute in Tübingen, and Google Research.
Okay, so let's start with the TLDR in a 2-3 sentence. What is this paper about?
So the paper is about combining the recent advances in neural rendering with the older classical 3D reconstruction methods. In particular, we want to exploit RGB data during our surface reconstruction. So the classic methods, they work by only looking at the depth, as in Kinect Fusion, for example. So whatever was not observed by the depth sensor is not going to be reconstructed. Other methods like bundle fusion do also look at the RGB data, but use it only for tracking and not for the actual reconstruction. In this work, we observed that RGB data, so the color data, actually does have a very high quality information that is not available in the depth frames. So, for example, if you capture reflective surfaces or black surfaces or many other kinds of surfaces, they do not appear in the depth maps, especially thin surfaces like some chair legs. They are not in the depth frames, but they are clearly visible in the color data. So in this work, we want to exploit this information to also get a 3D reconstruction of the surfaces that are not in the depth data, but are still visible in the color data.
Mm-hmm. So why is the problem of surface reconstruction important?
Surface reconstruction is important for various use cases like content creation. At some point in the future, we want to be able to just take a camera and record a real environment and maybe put it in a video game or use it for AR, VR, or virtual museums, and there are many different applications where we would like to display real content in some virtual environment.
So you kind of touched on this, but what are the main challenges? So you said that first thing is that RGBD, there are some places where you don't have depth, so use the RGB. What other challenges are in this problem?
So the main challenge is that the data is not perfect. As I said, the depth might be missing from the depth data, and it's also quite noisy. So that's the main challenge to solve. And the other challenge is even with it's not perfect, but let's call it perfect color data. It's still difficult to develop a method that can infer 3D geometry from the color data alone, since the problem is highly under-constrained, especially in textureless surfaces. So in case you have a textureless surface that also doesn't have depth data, that's pretty much impossible to reconstruct, because physically there are many different combinations of geometry, material, and lighting that could produce the same image. So I still see potential in the for future work on this. Maybe using some priors, because we humans are pretty good at figuring out what indoor areas look like offices, people's houses, and so on. And this knowledge could be used in future work.
And before we dive in, so just in like 2 bullet point sentences, what are the main contributions of this paper?
The main contribution of this paper is extending the NeRF formulation for volume rendering, so that I represent geometry as a signed distance field instead of a density field, and also use depth data to further constrain the reconstructed geometry. And also the joint optimization of geometry and camera poses. So I use the camera poses from Bundle Fusion as my initial camera poses, and then further refine them in the optimization process.
So before we dive in, let's just touch on a little bit about related work. So before a reader comes to read your paper, which 1, 2, 3 papers should they read first?
So the first paper that they need to be familiar with is the NeRF paper, because we build on top of a NeRF. Our method contains a rendering part that's pretty much the same as the volumetric rendering from NeRF, but we formulate this in terms of a signed distance field instead of a density field. And I think it's important that the reader first knows how the NeRF paper works in order to understand how our paper works. The next paper I would recommend reading is Bundle Fusion, because for the most part we compare our results to those of Bundle Fusion, and Bundle Fusion is also needed to initialize our camera poses.
Okay, so now let's dive in. What is the key idea and how do you do it?
Okay, the key idea is we take the NeRF framework, but instead of learning or optimizing for a density field, we optimize for a signed distance field. Using a signed distance field allows us to reconstruct better geometry, because in terms of geometry, the density field that is optimized by NeRF is too noisy. So it produces amazing novel view synthesis results, but the underlying geometry is pretty noisy. So we take in terms of 3D geometry, a more classical approach with the signed distance field. And the problem that we need to solve is how to combine the signed distance field with the volume rendering. So NeRF renders images by accumulating density over a ray, and then turning this density into some alpha values, which give the percentage of light that is reflected from some point in space towards the camera, and then further turning these alpha values into weights. Then the final rendered color is just a weighted sum of the color of each sample on the ray. And this weight function is roughly bell-shaped, with the maximum on the actual surface. So what we do is we go directly from the signed distance values to a weight function, and so any kind of weight function should in theory work as long as the maximum is on the zero crossing. So here we decide to go for the derivative of the sigmoid function, which is just the product of two sigmoid functions, like sigmoid of x times sigmoid of minus x. and also scaled by some parameter.
I just want to take a little step back, right? So I want to know what's your input and what's your final output. Okay. So your input is obviously an RGB-D sequence, right? And what's your output then?
The output is going to be the signed distance value and a color value. So similar to the NERV paper, which has density and RGB, we have SDF and RGB for every sample point in space.
Okay,
and,
so you have RGB-D sequence as input, and you produce like a signed distance function value with a color value for every point in space.
Exactly.
Or
and
rather,
these
every
can
point
be
close to the surface, right? Because it's a truncated, you're using a truncated version of the signed distance function, right?
Yeah, and these values can also be accumulated over an array to produce an image. So that's our predicted RGB image. And on this image, we can apply a loss with the target image. And for the signed distance values, we don't accumulate those, but each sample can have a loss since we know the depth for each of the pixels. So for the ones where we don't have depth, there's no loss. But where we do have some observed depth, we can apply a signed distance loss to each of the samples on the array.
Right. So you have several losses here, right, to optimize this entire thing, right? You have your signed distance loss, then you have your RGB loss, and then you have the third loss, which is...
Yeah, so there were like kind of two signed distance losses, but we differentiate between them. So one was in the truncation region, where we say that the signed distances need to be between 0 and 1. So this is a normalized value in terms of physical dimensions. This was 5 centimeters in most of our experiments. And then everything between the truncation region and the camera is considered free space, and it needs to have a value of 1.
Right. So you have 3 components in the loss. One component, so you have several losses, right? You have your RGB loss, where you have your input image and you want your output color to match. Then you have 2 elements in your signed distance loss, right? Because you basically separate into volumetric regions that are close to the surface to have one loss that you want to match the distance from the actual surface. Whereas if you're further away, more than 5 centimeters, you don't really care about the actual distance value. You just want it to be labeled as further away. So it's either -1 or 1 if you're inside or outside or closer to the camera or further away from the camera.
It's actually always +1, since I can apply the loss only between the camera and the truncation region. Right. Inside the truncation region, I go from 0 to -1 for another 5 centimeters. But beyond that point, I don't apply any loss, since the ray might actually be intersecting multiple surfaces. Like, let's say, the desk and then the floor underneath the desk. And I don't want this to be considered inside the surface, since I don't actually know if there are any other objects beyond the first one.
Right. Okay. That's an important point. You said before that you're using the bundle fusion cameras at initialization. So where do you use that and how do you optimize for that?
So I run bundle fusion in advance to get the camera poses. And then I refine the camera poses during my optimization. We use bundle fusion to get an initial estimate for the camera poses. And then during our optimization, we actually sample points on the rays in camera space first, and then have a transform to world space. So we use the estimated poses to transform the samples to world space, and then there's a second, let's call it correction transformation, which can be optimized for. So these are 3 rotation parameters and 3 translation parameters. And here we track gradients with respect to these parameters. So in the end, after applying the laws, the gradients also get back propagated to these parameters. And by this, we are able to refine the camera poses.
So all of the parameters that you use here are basically networks that are implemented as a multi-layer perceptron, right? There's nothing fancier than that.
Exactly. So we actually use the NeRF MLP, an exact copy of the NeRF MLP. The only difference is that we lowered the number of frequencies for the SDF network by 2. So instead of 10, we use 8. And that gives us slightly smoother surfaces.
And once you get this SDF, you basically reconstruct the surface using what method?
I reconstruct the surface using merging cubes. There are minor differences between different implementations of merging cubes. I use the implementation from bundle fusion, which also has some interpolation functions to produce smoother surfaces, and this was actually important to have a fair comparison with bundle fusion itself. There is also we call it deformation field. We don't know if the camera intrinsics that the method was initialized with are correct. So we also optimize for the intrinsics themselves. And this is another smaller MLP that takes as input pixel coordinates and as output produces some offset vectors. So for each pixel in the image, it tells me, okay, a sample maybe the pixel 2 positions to the right and 3 positions up. So it's an offset in image space.
And you also had like a correction latent code that you were learning.
Exactly. So since the target images don't have constant exposure and constant white balancing, I added a latent code here so that for each frame I can kind of learn these inconsistencies. And in the end, produce more consistent color images. And this was inspired by the NeRF in the Wild paper.
Okay, let's move on to the results. So how do you even evaluate this kind of problem?
Yeah, that's a very good question, since evaluation of these methods is not trivial at all. Some common metrics that I used are IOU or normal consistency or chamfer distance, also a bit newer, the F-score. And each of these methods has its own advantages and drawbacks. And even independent from the metrics, the question is, what exactly do I evaluate on? So when it comes to all the neural methods, the deep learning methods, they will produce some geometry in areas where the networks were not sampled. So let's say I have a room and I have some walls, but I don't know the exact bounding box of this room. So when I sample my volume to get a geometry reconstruction, I will get some geometry behind the wall, maybe under the desk if the space was not sampled, and behind different objects. So the question is, should we take these into account in our evaluation? And we said that it actually doesn't make sense to have these areas contribute to the final error. So what we did was some frustum culling. We go over all of the cameras that were used in the optimization. And we keep only the surfaces that were seen by at least one camera. So everything that is outside of all the frusta and that is covered by other objects is going to be culled away. And then we do the culling for both the ground truth geometry and also for the geometry of our method and all the baseline methods. And then we evaluate on these culled geometries. And the evaluation metrics that we used here were the chamfer L1 distance, then We had the F-score, for which we picked a threshold of 5 centimeters, and the normal consistency. So these were evaluated on point clouds that were sampled on the mesh. And we also voxelized the mesh with 5 centimeter large voxels, and then reported the IOU score as well.
One of the things I like a lot about this paper is the qualitative results. So this is an audio format, so we can't really show it here, but it's definitely one of the things that are best visualized, one in the paper, but also in the project page as a video where you can like really see it in action. So definitely go and check that out. So were there any interesting fail cases or some surprising results that you had?
Okay, for the fail cases, there wasn't any particular fail case that pops right into my mind, but there are examples where the method struggles more. For example, for color reproduction, I get worse results than with NERV or other more recent novel view synthesis approaches. But since our focus was on geometry reconstruction, we were not really bothered by the qualitative results of the synthesized RGB images. It was only important that they are good enough to guide the geometry reconstruction. And here we actually see a lot of room for further improvement. And I believe that it's possible to design a method that will produce both better geometry and better color than what we currently have. Then another problematic area are all the hyperparameters. So the method results are affected by parameters like the badge size or like the width of the truncation region. And it's a bit difficult to figure out the perfect parameters here. We did do some ablations, and we have some intuition of what works well and what doesn't work well, but these are also a little bit scene specific. So if you have a huge room, you might not have the resources to reconstruct everything at a, let's say, 1 centimeter resolution. But if you are reconstructing a very small object, then you might want to change the parameters that we use, because they may not work for high detail on small objects.
Yeah, I think one of the things I like most about this paper is the fact that it's one of those papers that tries to combine two tasks that are usually dealt with separately, right? So usually you either try to just reconstruct the geometry, or you try to get like a good synthesized image. And in this case, you're kind of combining these two problems into a single problem where you do both at the same time. So it makes sense that there is still a way to go here in the sense of getting both of these problems solved correctly. And it seems to be like the right way to go, right? Because this is like what happens in the real world, right? You have the geometry and you have the colors and the way they interact with the light. This is how it affects what we see as humans.
I totally agree.
Is there any other results that we haven't touched upon?
I had some experiments with sparse depth. So, for example, color-only methods like ColMap that can give me sparse depth. Mm-hmm. And there it was very difficult to reconstruct textureless regions.
I think this is one of those papers that has a supplementary material almost as long as the paper itself. So it's definitely worth checking out some additional results and things that you provided there. All right. So conclusions and future work. How do you see the impact of the paper going forward, and what interesting projects do you see emanating, or are there any papers that followed it?
So the paper was just accepted to CVPR something like a month ago. So there aren't any follow-ups to my paper yet, but there were a couple of other projects that were done in parallel. like the newspaper or a couple more papers that reconstruct geometry only from RGB images and use a method similar to NERF. So it's definitely an interesting field that many people are working on. The follow-up work that I see is work that builds up on this idea of using color images together with depth images during geometry reconstruction. And I believe that that's the way to go, that depth information can be useful for novel view synthesis. Especially if you have a limited number of viewpoints, you might not be able to optimize a good representation that can also extrapolate to more extreme novel views, and this is where the depth data can help. But also the other way around, the color data can help us with geometry reconstruction in areas where we didn't get any depth data. So I believe that this is a great research direction with a lot of potential in the future.
Yeah, sounds like really interesting projects. You know, when early career PhD students, they are looking for their next project. So it's really hard to know what are the good directions. It's always good to hear someone that just spends such a long time in the mud doing everything. So it's really important for the future direction of research in this area.
Yeah, then you see which areas were problematic and what can be improved on. So in our case, that would definitely be the novel view synthesis part, which we pretty much ignored in this project, but also some real-time reconstruction application. Since this takes several hours to run, and there were many NERF follow-ups that make inference or also training faster. And I believe that our approach can be combined with these approaches to, at some point, make the reconstruction real time.
Yeah, this would be super interesting. Okay, moving on to my favorite part of the podcast. What did reviewer 2 say? Please share some comments you got from the review process and how they made the paper better.
Okay, so the review process was somewhat noisy. I actually went through 2 reviews since the paper was initially rejected from ICCV. Review 2, from what I remember, didn't say too much. At that time, it was reviewer 3 who unfortunately rejected my paper, but also gave the most feedback about what can be improved. And the general comments were that the results are great and the method is novel. They liked the idea of using depth together with color and also the formulating the NERF approach, but they didn't like the lack of quantitative evaluation at that time. Since at that time I evaluated only on a single scene, and I didn't do all of the ablations that I have in the paper right now. So the paper was rejected for that reason. But then for CVPR, I added an additional 8 or 9 scenes to the paper, and also added several ablation studies. So this time there were 0 complaints about the actual evaluation, but the reviewers weren't too happy with the theoretical explanation for the method. So they felt that either it needed a bit more theoretical support, or that some aspects could have been explained a bit better. So I'm not sure whether we made it slightly more confusing when we rewrote the paper, or it's just a part of this noisy review process.
Yeah, I think one of the important things when getting a review that essentially rejects your paper at the end is to write the parts where the author can do better. And it sounds like this is what happened in the first review cycle, right? The reviewer rejected the paper, but they said, well, I think it's a novel idea, so you should keep going. But these are the things that I think are missing to get it like over the edge. And this is super important. Not all reviewers do it. Like sometimes it's just okay, this is a reject, and they don't really specify how you should improve. And I think a part of the whole review process is actually to help authors get their message across, because it's obvious that everybody's putting a lot of work into it. And it sounds like the paper did end up being a lot better, right? Because there's a lot of experiments, many ablations, like a lot of things are much clearer now. As for the theory, well, we're working in this, very application-oriented field. Everybody wants to have more theory, and it's good that, you took that into account, you revised the paper, and it got in. So I guess you managed to answer the requirements at the end, right?
Yeah, the reviews definitely made the paper better.
Okay, Dejan, thank you very much for being a part of the podcast. And until next time, let your papers do the talking. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.